All right, welcome to the second part of the AI lecture series. In the first part, we tried to focus a lot on the math part of the neural network. Got some feedback in terms of go easy, we need some time to go back and refresh math. So what I'm doing is, at least for this presentation, for the second presentation, I'm trying to keep the math really minimal, but I would pretty much start bringing it back from the third or fourth series, mostly the third one. But this is kind of a continuation of what we did in the first part in terms of everything that we tried to understand on the neural network part. As a quick refresher, I think we tried to set up a motivation in terms of why neural networks. We understood the structure of the neural network. We went ahead and tried to understand different components of the neural network. In this series, we will get a bit of understanding in terms of how to set up the data partitioning, what does regularization or generalization mean, what does curve fitting mean, and so on and so forth, right? In the tradition of moving forward, which I probably need to click here, we will start with the trivia. Last time I tried to actually put more slides around trivia, but going forward for every lecture series, we'll bring in a little bit of trivia. And each of the lecture series mostly will build on itself from the last series, but there will be certain lectures where I'll just go work on different components of machine learning algorithms, or I'll work on statistical modeling. I'll introduce comparisons between different types of dimensionality reduction or regression or neural network architectures. So while I try to be continuous, sometimes it'll be going back and refreshing and then moving forward. The trivia, the reason I put up this trivia is just to state that not anytime in the near future AI is going to take over. Primarily because with 300 calories, you get about 100 trillion connections, and there are about 6 billion of them on planet Earth. And that's a lot of compute power, and there's a lot of creativity in there. So there's still a lot of potential with that kind of infrastructure, with that kind of volume, that machines will take some time to take over. But that said, if superintelligence need to happen, it will happen really quickly in a flash of time. When there is sentience and then there's awareness, from that point for the machine to take over, it's probably milliseconds to an hour, right? Because of the speed of the infrastructure, it's not just the capacity. As said, the agenda is, let's quickly refresh what we learned last week. Do you guys remember these functions? What each of these components stand for? We said there is a neuron, there is a connection between two neurons. All these connections can be layered, or they can all be in a single layer. There is an input for the neuron, there is an output for the neuron. The input needs to be combined in a meaningful way along with the weight of that connection and handed over, and that concept is called the transfer potential. And once the transfer potential is handed over to the neuron, there is a compute function hidden in the neuron. We call it as an activation function. The activation function has to be nonlinear, and it has to be differentiable. Why does it have to be nonlinear and differentiable? Anybody? Nonlinear, she says nonlinear because, Saraswati, right? Sarah says nonlinear because linearity it's not very creative. It's boring, it's straight, it's dull. It cannot exhibit complex behavior. Right? The curvature is where the complexity is. The curvature is where dimensions are. The curvature is where you can actually go ahead and do interesting things. But why does it have to be differentiable? You're very close in that answer. Why else does it?
It makes it trainable?
Why does it make it trainable? Hemant says it makes it trainable. Go ahead, David. Well, it's a bit more complex. When you actually have a tensor, you want to compute a Hessian. If you don't have a tensor, you can compute the Jacobian. If you don't have a matrix, you can still compute a gradient. When you don't have multiple variants, you can compute a derivative. But that becomes too mathematical. But the real reason why you want to actually go ahead.
The magnitude of the error tells you how far you were from the right answer.
Exactly. The magnitude of the error. We want to actually get a derivative or a slope or a gradient to say how far are you from the error. Well, you can actually compute that by taking the absolute values, right? But that does not allow you to actually go back and scale the weights. If you want to scale the weights, and the concept of scaling the weight is called? Awesome. Tomas, VP Growth, backprop. Primarily, if you want to really go back and change the weights, you need some input beyond just how far are you from the error. And that input is the gradient. And that gradient can be calculated only if your activation function is differentiable. We learned this last week. I know the math, we're just ingesting it. That's why I'm not going to do a lot of math on this one, but we're going to rehash the concepts, right? Now, which one? So I've already written the activation function over there. Can we identify what is it called? You can have different kinds of activation function. That equation is a sigmoid, correct? Who said that? Nathan? No? JD? You can have different types of activation functions. You can have different type of error functions. You can have different types of summation or transfer potential. There is no reason why it has to be this, but this was the simplest on which we did the math, right? And we said the backprop or the backpropagation requires a way to actually learn this movement from here to here. I don't know how to write it anymore. Nathan, probably you need to help me. Oh yeah. So the way the error gradient moves is from top to bottom. We are actually trying to find minimal, or we are trying to find we are trying to move the error to 0, right? That is primarily because of how the equations have been set up. We couldn't directly say y equals x times w, where w equals y divided by x, if you remember. We cannot do straight math on gradients. Instead, you actually negate that with the error and see how far is it with the error. And the direction of the error being minimal is always on one of the extremas, right? It cannot be at the maximum, it has to be at the minimum. And we use the gradient to actually find the minimum. In this session, we're going to learn a little bit about feed-forward neural networks. That's exactly the concept that we learned in the last session. It's just called the feed-forward neural networks. The architecture of the feed-forward neural network does not have to be complexly layered. It can just be 2 layers, input layer, output layer. But that's not very interesting. You need to at least introduce one hidden layer, right, where there's a hop, there's at least some amount of hyperplaning, as you call it, where the knowledge weight gets an opportunity to demonstrate more than one step of nonlinearity. You can just have one single neuron which is nonlinear and still get some interesting behavior from the nonlinearity. And that sigmoid is called the logistic regression. In machine learning, you already do logistic regression. But one neuron with a lot of compute power within that one neuron trying to actually filter out the variance versus many million neurons, each doing nonlinearity, was where the power was, because each one of it outputs something, and then the network is trying to average it out, right? The feed-forward neural network has certain characteristics. All nodes are connected in single direction, moving forward. It's a directed acyclical graph. There's no cyclicality, at least in a feed-forward neural network. It's a simple network with no hop. That means you would not see connections that goes like that. The connections are always moving forward. It is many-to-many connections. In other words, you'll notice that each of this neuron is connected to every single neuron in the next layer. It has all neurons from the previous layer. Neuron in one layer, that is, let's say you have a neuron here, it's connected by all neurons in the previous layer. So when you say many to many, that's the characteristic. The reason we are doing this is because whenever an independent variable comes into the first layer, it has possibilities of many paths to take. You're just increasing the possibilities of the number of paths that this can take before it reaches the output, which allows you to actually go ahead and model weights for each of these paths differently, right? So that improves the creativity of the network, that improves the possible modeling capability of the network. Each one of this is called a parameter. How do I erase this thing, Nathan? I'm sorry, last time we had a different setup. Yeah. Oh, maybe clear drawing, I found it. Thank you. And I'm stuck with color red, so bear with me if it's Nitesh. The hidden Markov model has different properties. When so we're going to do a HMM versus a neural network comparison in future presentations. But the HMM has a different type of properties. It has a Bernoulli trial. It has you need a distribution to actually set up your hidden model, right? Here, so there's determinism versus non-determinism. We'll get there. But if you want to actually visually try to compare the models, geometrically you can say it's similar to, but it's not the same. We said the activation is nonlinear and differentiable. You can have more than one output, by the way. So if you notice right now we are having a single output, but there's no reason why you should have a single output. You're actually setting up a single output for a hot or not, yes or no. So the single output can actually have a sigmoid as a, so this output can also be a sigmoid, which actually can it can be a tan H like this, -1 and +1, or it can be a sigmoid like this, which is 0 or 1, which says yes or no. Or you can have two nodes, one node giving you 0, another node giving you 1, right? Or you can have multiple nodes. Now, the neural networks can be, the exact same neural network can be trained to do two different types of activities. One is called classification, other one is called regression. What's the difference?
With classification, you're putting things into discrete categories, and with regression, you're trying to figure out a value or a numerical representation.
Exactly. In classification, you're trying to rate and rank, categorize, or trying to identify some kind of flavor, taste, species, assignments. In regression, you're trying to forecast a number. It's a real number, right? You're trying to forecast time series for signal processing, for control systems. You're trying to forecast market indexes, right? It's exactly the same neural network. That's the power of artificial neural networks. You can understand the math behind it. You can understand the architecture of it. But the way you set it up and how you train it and what activation functions, cost estimates, and your transfer potentials you use actually can be used to train the exact neuron to do different things, as against trying to learn SVM, PCA. As against in classical machine learning, you had to kind of tailor different algorithms to do different things. In artificial neural networks, you understand one tool set, which is what nature pretty much evolved into, to do multiple things: pattern recognition, speech recognition, regressions, classification, which is why some people say the AI winter is over, given the deep neural networks, right? Yet to be seen.
You use the term deep neural network. What does that mean exactly?
That means multiple layers. Deep learning means more than one layer. You're going deep. So the holy grail is to see how deep can you go by increasing the number of parameter paths. And the depth is not just the number of parameter paths, right? Because you can get the number of parameter paths by putting all the neurons in the same layer. But depth actually gives you a concept called hyperplanes. What happens in the first one, if you remember, the layers actually allows you to learn first at the core, finest level. Like it tries to understand the small contours in the curve, then the curves get put together, then it tries to understand a feature like the eyes and the mouth, then that gets put together, and then the face. So that hyperplaning is super important for deep learning.
So with supervised learning and deep learning, is there a risk of going with many layers and just over-specializing it to the training set?
There is always a risk of doing too much, either in terms of layers or by throwing a lot of neurons or by increasing the parameters. The concept is called numerical conditioning. How do you make sure that the neural networks are stable enough, efficient enough, trainable, coachable, and consumes the least amount of resources, 300 calories, right, to actually get the job done? That is where the rest of the industry is actually working on in terms of new research paper. But yes, there is something called too many layers, which actually increases the complexity. We're going to learn that in this session.
Please, one more question.
Yeah.
before we move forward.
Yes.
You mentioned that the classical machine learning use different algorithms for different tasks, whereas with neural networks you can just use one tool. Right?
Yeah.
So is the world generally then moving to using neural networks for everything?
Slowly,
Okay.
primarily because with classical machine learning and with specialization, you can actually humanly tailor a lot of things with models like SVM. If you know how eigenvalues work, you can do certain things, like your SVM, your SVDs, your PCAs. They're special purpose, but you can control that smaller black box. There's less things that can go wrong there. With neural networks, it's extremely powerful. It actually starts modeling both the data and the noise. And the concept of regularization, that's what we're going to learn today. It's so powerful that it's hard to control, right? And I'm probably exaggerating a little. The power is based on how many parameters you throw, what's the size of the architecture, what's the depth of the architecture. So you can actually control it. You don't have to be scared of it. But hyperparameter tuning or trying to make the model stable and behave the way you want it to behave is less obvious in neural networks than classical machine learning. So people are very comfortable doing the things that they know, but when you slowly move towards neural networks, which is pretty much everything today that was done in the past using classical machine learning, is being done by neural networks. And there are different ways to set up neural networks. There's convolutional neural networks, there is feedforward neural network, which we are learning today, there is recurrent neural networks, there is reinforcement learning. Everything uses neural network. But suddenly the classification or types of architecture of neural network has branched out. But the fundamental notion of the neural network that you learned last week and that you're going to learn this week has remained the same. And neural networks are solving NLP problems today, right? All your neural machine translation from Google, what is it? It's not your age-old classical NLP anymore. It is neural networks. Your fast text is a neural network, right? So signal processing and vision, pretty much nothing comes close to neural network. But when it came to NLP, your classical NLP was always doing good until the new models on NMT, neural machine translation, came in. Even that place is taken over, right?
So are there still areas where people are still using classical models?
We pretty much use classical models all the time because one of the things about classical models is it can be a pre-processing step to reduce some amount of workload for the neural network, especially the compute, especially the dimensionality reduction, that if you as human can do it with the knowledge of the data and the taxonomy that you have using classical machine learning, and then hand over the most cleanest signal to the neural network, then you will actually improve the efficiency. So it depends on how you want to build this agency. If you're like, people across the pond who has a large amount of money, a lot of data, then you can just say, I'm going to build the largest neural network, I'm going to throw data at it, and I'm just going to do math modeling around it. And then the network will learn everything. So the network can actually start doing phased elimination of noise. The network will learn how to actually do feature modeling, then it hands over the right features. I'm going to show that next week in terms of how can you use neural networks to do feature modeling by itself without you as a human being who's doing feature modeling today, where we are hiring machine learning engineers and data scientists, can be done by the neural network all by itself. We're going to make ourselves redundant and then move forward to do something cooler, right?
I was going to say, one disadvantage of neural networks is they're not always very comprehensible. And if you really want to understand what's going on, other models might work better.
Yeah. Videsh?
With respect to classification, right, whenever we take a data set to basically train whatever model we're using, there's a very high probability that the model gets biased only to one side, right? Let's say if we have a simple classification of 0 and 1, and if the data set has more of, say, zeros and 1, then how would supervised learning affect the model? Because we'll have a lot of false positives, and basically you would not have a good model that can classify between 0 and 1 more independently than its biased learning.
You may not have false positives. Class imbalance does not necessarily mean that your data has false positives. That is the truth. The truth in the data should speak for itself, right? Until and unless you're actually sampling that data. The bias comes from sampling in a very wrong way. But if in the world the data is full of zeros and very few 1, that is the class imbalance. And there is a way to actually train networks of class overlaps, class imbalance, right? You create more 1s, you reduce the zeros. We'll come to that now, probably series 3, series 4. Tomas.
You just mentioned that the neural networks are used everywhere, more and more, which makes sense. But the area where I'm surprised to hear that is, in fact, prop works through gradient descent. Doesn't mean by default neural networks find local optimum rather than global optimum?
Yes and no. You can actually set up a stochastic gradient descent with just slides and stops. You can find momentum which slides, goes up, and finds a hill with a bigger ball. You can do simulated annealing. There are techniques. This is not a neural network problem. By the way, gradient descent, trying to find local minima, is not a neural network problem. That's a classical machine learning. That's a statistical modeling problem. Finding local extremas is a statistical modeling problem, right? Depending on where you start the hill climb, will only find the local hill. But how do you make sure that you hop around? MC, there are techniques, or simulated annealing. I'm going to cover simulated annealing as much as possible, where you can say, I am increasing the possibility of finding the global maxima or the global minima. So we said there are two types of modeling capability: supervised learning and unsupervised learning. In supervised learning, you need a large amount of data to train the model first before you can deploy the model to service. In unsupervised learning, you're not training the model, you're letting the model loose so that it can find the contours or the clusters or the topography of your landscape. You're just saying, okay, here, expose the internal topology of your data. That's unsupervised. You're not really training the model to find something. But in supervised, where you want to classify something, you want to regress something, you first need to train. And for training, you need a large corpus of data. That can be one downfall of neural networks, right? When you're actually doing supervised learning. You create data that is not there sometimes so that you actually eliminate the bias in the sample that you might have. You might not have all the data in the world. You might have only few cat pictures, or you might have only few votes from people of what they want to eat for lunch. But you just don't train that way, right? Your pictures might not be diverse. It doesn't have diversity where it has picture of all ethnicity. And when you're training your models, it might learn wrong behavior. And this has happened in the past. Google Photos, I don't know whether you remember the disaster. It started tagging people as gorillas. And that was primarily because of bias in the training data, right? So we have to be very careful. There are some ethics that you have to follow when you actually do any kind of machine learning. And those ethics actually are necessary to eliminate bias in your samples. When you're actually doing the training, both input and output is actually expected, which means you need to say, what am I going to train? Cat pictures. And a label to say, when this picture comes in, I want you to actually take a neuron, which is being assigned for cat. That will be neuron 1, neuron 2, neuron 3, one of those. So if you have 3 output neurons, cat, dog, and I don't know, everything else, when the cat picture comes in, you want the data of the pixels of the cat and an activation for the cat neuron, the end output, right? That is required when you're actually doing supervised learning. The output data does not necessarily have to be static. It can be computed, but once it's computed, it remains, and that's called a target approximation function. But we need to remember that training data is noisy, that the cat pixels might contain some background noise. It might be on a tree. It's not very easily identifiable as cat because it's a picture, a long shot picture, or there are different types of cats, or there's sampling errors in the camera which has introduced the noise, or primarily your pixel is grainy. So all of this is called noise. Same thing with speech. Recording might have noise. Same thing with text. You can have spelling errors. You can have grammatical errors. Right? Everything has errors or noisy. And we have to be aware of what's the probable percentage of noise that your data might have, which you can eliminate using classical machine learning techniques, or throw it to the neural network and try to eliminate it within the neural network using a scheme called regularization. Both are okay. But if you can actually eliminate noise as much as possible, all right.
Wow.
Well done. We just signed our director demand intelligence. That's what that is. Yeah. Because of the power of the network, it's going to learn both the signal and the noise. That's the trick where classical machine learning comes in as a pre-processing, right? Or you have to be really good at neural networks where you just go and regularize it. Now, go ahead, Sarah. Feedforward neural network. That's the backpropagation, right? So primarily when everything's moving forward, you first, if you remember the math, were you there in the previous? So the first, I don't know how to go back anymore. Not used to this. Yeah. So the first error derivative is calculated at this node. Then the weights are changed. Not changed, but at least the input is available for how much weight has to be changed over here. But before making that change, then you say, okay, what's the gradient that I need to pass to this neuron? But before you make the change, you say, what's the gradient I want to pass? So you calculate the gradient that is required to be changed, which is called backpropagation, through and through, until you have the gradients of all the weights in the entire network. Then you apply it one shot, and then you validate once again. As in you during training. So there is a training cycle and there is a validation cycle, right? When you iterate, when you put the network to service, you call it the first iteration, right? You send the first cat picture in, then you say, what's the error? You just keep the error. Then you send all the cat pictures in. That means you go through, like if you have 500 cat pictures, what you can do is you can say for every cat picture you can take the error and you can go back and change the gradient. But these are all different cat pictures. So if you send the first cat picture, there is an error, you go back and scale it. The second cat picture is a completely different cat picture. So that is going to keep destabilizing the network. Or you take 500 cat pictures, run it through the network, collect all the errors, and then use that full batch and some form of cost function which computes not necessarily a mean, you can compute the mean or some other cross-entropic measures on it, and then apply that. Or you can also do mini batch, saying I know I have 500 and I'm going to take 50 cat pictures, and every 50 iterations I'm going to change the error gradients. Once you're done with all the 500, it's called an epoch. One epoch is done. It has at least seen each of these cat pictures once. But you don't stop there. Now you can actually go second epoch, third epoch, fourth epoch, 10 epochs, until the error is actually stable. I would revisit backprop once again when the math is clear in a couple of days, in a couple of weeks.
One day our brains don't do backprop. The original neural networks only work feedforward the way neurons have been shown to do. So it was kind of a stumbling block for people to realize that backprop is really powerful, and our brains don't do that.
That's a theory. We don't know whether it does or it doesn't. We don't know what our brain does. And that theory is based on, you show the kid a cat picture once, and then the kid will recognize that cat for the rest of their life. I'm like, yes, right. Try that. Because for all different species, it doesn't work. And probably there's something called a wake-sleep cycle. There's something called regurgitation. The brain, we don't even know what the brain does. I mean, I'm not a neuroscientist, so time out, have no clue. But yes, that's a good theory. And that theory probably leaves out the fact that there are 100 trillion parameters in the brain, 100 trillion, and we don't even know what those 100 trillion parameters are doing, right? And we compare it to probably 1 million parameters. But that actually excites us to say, what is it that we can do in terms of showing the picture once and not running the picture again through an iteration, but making the wake-sleep cycles actually remember it. So that's when the concept of attention networks, that's when the concept of memorization actually comes in. What is memory, right? Either way, good point, JR. Moving forward, this concept of noise actually introduces variance, right? We need to understand this slide a little better for all machine learning purposes, right? There is variance and there is bias. Now you can have the neural network learn every single data point in your input. We call it as the best fit, or it's called overfitting. When your neural network actually learns every single data point, we call it as overfitting. Let me just first skip to the, is this visible? Yeah. If you notice on the rightmost over here, the curve fitting goes through every single data point. This is called overfitting. This is actually useless because we don't know if I want to use this model for prediction, and if I want to say where is the next data point, it's going to be very difficult to predict. Is it going to be here on this line over here? Is it going to be on this line over here? Is it going to be on this line over here? Because I mean, or is it a sum of all of this? Then the summation of all of this is a linear model, right? So that's not very helpful. This is not very creative as well, right? Instead, the best fit models actually this would predict the next point over here. This would predict the next point over here. This can actually give you a quadratic where the next point can be here, here, or here. We don't know. It's actually learning the polynomial equation. Why does it do it? What's the use of it? How we should not learn every data point, how we should not learn a function is what we're going to learn. For that, let's understand the variance and bias a little bit. This is a good place to be. That means we are actually saying there is low bias, low variance. This is a bad place to be, high variance and high bias, right? It's impossible to, it's very easy to be here. It's almost impossible to be in the first place where you have low bias and low variance because it's a trade-off. You can either get low bias or low variance. You cannot get both. So what you need to find is this equilibrium, right? This optimum point. Now what is this curve? This curve actually talks about a concept called degrees of freedom, right? We'll understand what this degree of freedom is, but notice that as the complexity of the model increases, that means as the degrees of freedom of the model increases, the variance increases. That means the ability to learn everything about the noise within the system also increases. It also learns the signal. When the bias goes down, that means it's also learning the signal. If it's not learning the signal, you have a very high bias system. If it has learned all the signal, we have a very low bias system. If it is not learning the noisiness, you have low variance. If it's also computed the noise, you have high variance. So far so good? As the complexity of the model increases, which is this curve, or the ability to learn degrees of freedom, the model's ability to reduce bias and increase variance also increases, which will be this box. It will be somewhat near the bullseye, but spread. To actually make it not that dispersed, you want to reduce variance. For it to be towards the bullseye, you need to reduce bias. If you have a bias, the curve shifts. If a sigmoid, if you add a bias to a sigmoid, what happens? The curve just shifts, but the sigmoid remains, right? So what do we do? How do we, first, what is degrees of freedom? So let's, I don't know whether I can write on this slide. I'm not going to do much math. I've realized that we need a couple more weeks. But let's say I have, is this readable? Better? I have multiple features that I want to train. What is a feature? A feature of a wine, right? A feature of a wine can be its color. I don't know. You can describe taste into many different. Depending on the cultivar, you can actually blow up taste into viscosity and whatever, right? Let's assume I want to train the model on each of this feature. I send 10 or 15 features of a wine. I can actually take all the 15 features to model it. Or if you're trying to say, if you want to categorize an animal into a species, a dog into a species, and you have the lifespan of the dog, the weight of the dog, the color of the dog, the height and width of the dog. Let's say I have only these 4. Those are called features. And then the output will be Chihuahuas and German Shepherds, and those are all the classes. Now, I have x1, x2, x up to the xn as features. We say the degree of freedom of this is n minus 1. And let's understand why it's called n minus 1. So I have if I have n features, I have a degree of freedom n minus 1. To understand that, I can represent this as a vector, which can also be represented as, let's assume if the mean of this is some x bar. The mean of all of these values of this vector is some x bar. Then I can first add and negate. That's a simple trick in math, right? If I have x1 to xn, I can do this. I mean, this is exactly the same. I'm adding and negating a vector, correct? But this is called the residue. This vector, this is the component vector. This is orthogonal, and this can also be written as a unit vector, right? You can take the x bar outside. You can write it as a unit vector, and this is your residual vector. So this has a degree of freedom 1 because the only thing that is a variable over here is the x bar, that is the mean. So we say the independent variable can only change in one dimension, in the dimension of its mean. That's the component vector, but that's orthogonal. The projection of it on its subspace is of dimension 1. We'll understand these concepts later, right? If you're done math, that's what it is. But using this, we can say the constraints on this matrix is the same as do we agree? This is equal to 0. When you take the mean of a vector and go to every single component of that vector and reduce it by its mean, the sum that you get should be 0. And this is the interesting part, which actually tells us that if I get to know the values up to xn minus 1, which is equal to 0, then I can predict what xn is. Correct? So if I say I have 1 plus 2 plus 3 plus dash equals 0, I can predict what the dash is. But if I have 1 plus 2 plus dash equals 0, the probability, I cannot, so there are 2 degrees of freedom. I cannot, I mean, it can be any different numbers. But as soon as you bring it down to one dimension that can be predicted, then the degrees of freedom actually comes down by 1. Hence we say that for a component vector which is input xn, the number of ways it can actually move in that dimension is n minus 1. That's how we arrive at degrees of freedom. So the complexity, look up on degrees on freedom, or after the lecture series, I'll be able to help you further. During the next week, I'm around. Come and ask me. But the takeaway is this: that Nathan. Oh, that's you probably. Yeah, I'll actually zoom it myself. All right. The takeaway is this, that if you have 2 input parameters, the degree of freedom is 1, that's good. If you have 3 input parameters, the degree of freedom is 2, kind of still good. You have 15 input parameters, degree of freedom is 14, you're already getting into an icky territory, because it can actually, there are 14 dimensions, 14 different ways it can turn. And hence the complexity of the network is higher. Because it can actually model things in 14 different ways, it's going to model the noise, it's going to model the data, and it's going to model the variance, it's going to model the bias. Bias will be high, variance will be high. So the trick is to say, which of these 14 parameters will I pick up by reducing the dimension? The concept is called dimensionality reduction, which we'll learn in the next session, okay? But that optimal place is where we want to be, where the bias is almost getting to a low, the variance is kind of increasing, but if you increase the complexity of the network any further, then the variance will increase. So you want to stop the complexity of the network at the right place. We cannot try to replicate brain by throwing 100,000 parameters out there, because the complexity of the network is high and the complexity of the input. What we're talking about is the input complexity here, degrees of freedom, right? Not necessarily the network complexity. But the ability to pick many different parameters, which you will see here, for a complex network is extremely higher. So far so good. Any questions? Why is this important? This is important because you don't want your network to be doing things like this. Like it's trying to, classify literally every single dot out there. Not very helpful, right? Because When you train the network to do this, and if it has not seen certain set of events in the past, that concept is called generalization. What do you train the network on? You train the network on 500 cat pictures. That's the only pictures the network has seen, and it has tried to understand the cat looks like this, like how the humans see only one picture and then can recognize all the cats correctly or probably. The network has seen 500. If you keep sending these 500 cat pictures, it'll be perfect. It'll say this is a cat, this is a cat. But as soon as you set another cat picture which the network hasn't seen, then you want the network to predict it correctly, right? But that is based on how much of noise and how much of signal you've trained the network on. If a Siamese cat, and then you actually go ahead and send another cat, which the network has not seen, and it has learned the feature dimensions of how the cats look correctly, and if not the color, then it might probably do the right thing. But if it starts learning the color, the number of hairs on it, the number of pupil, the dots on the pupil, that's noise. You don't want the network to learn that a cat actually has the scar and it has to actually have a patch on its back, and you don't want the network to learn that. That's what is learning the noise. You kind of want a silhouette, like you want like a mask that the network wants to learn, and not overlearn every single detail, so like the length of its, the size of its claw and so on.
So when you mentioned this, right, let's say you're doing, say, X number of epochs over a set of 500 pictures, and we're confident that it's learned, right? So in the next set of examples, would you give a different set and you figure out if it's how accurately it's measuring, and then go back, and if it's not an acceptable number, then you go back and retrain the entire model based on the 500 pictures?
Yes.
Or you would include the test set also a bit to give it a little bit more dimensionality?
No, you retrain the network based on validation. I'm going to cover that in the next slides.
All that makes sense. But then in practice neural nets, so if you have some cat sitting at this angle and another cat sitting at this angle, and that's the primary thing, then the net will fracture them both very strongly. Like each part of the neural net will have like handle one type and another handle another type at the same time.
So the way you do that is you actually use windows. Instead of trying to learn the cat within the overall frame, you just actually go ahead and set up the convolutional neural networks. In the next few sessions, when I talk about vision, I'll talk about convolutional neural network. You start windowing, and in each of the window, you learn by flipping, so that you don't learn just one posture of a cat. I'll cover that. The characteristics of data on which you need to learn. And we just generally said that degrees of freedom matters. The more the degrees of freedom, the more noisier it can get. And the complex the network, it will end up learning the noise. But before getting there, here's a simple example. So if you have a cultivar as an output, that is what is the type of wine, and the inputs are like the alcohol content, the malic acid, the ash, whatever. I mean, the phenols and color intensity and hue, whatever. You have some kind of input. If this input is given, you should be able to predict what's the wine cultivar, right? The way the input is actually sent is through this numbers. All of this is a number. Every single input for the neural network has to be a number, a numeric value. It's a real number. As a fraction, it can be rationals, irrationals, doesn't matter, right? Now, look at the characteristics of this. The maximum value can go up to 14.83 on the alcohol. The minimum can go up to 11. Separately, when you look at proline, the maximum value can go up to 1680, and the minimum can go up to 278. Then you have some numbers like flavonoids, which is in 0 point some fractions. All of this is trying to send not just the signals, but the strength of the signal are all different, which is dangerous when you're actually training a neural network. Because something can be 1 million, another thing can be 0.03. So this concept is called feature scaling. I'm going to cover this in the third session, where what do we do when these are all numbers and the numbers have different strength that is going in to the transfer potential. Depending on one of the neurons which is activating the transfer potential, will do 1 million times the weight. The other neuron will do 0.3 times the weight. the network will be extremely imbalanced. So before you actually send values like this, you need to do a concept called feature scaling. I'm going to cover the math of it in the next section. But the data characteristics is important for you to remember. But not just that, you also need to train it differently. You just don't send, if you have like 500 rows of these values, you don't just send all of them, right? You partition the data. You actually say, I'm not sure whether this is visible, you can actually set up a validation set and a holdout set. If you have 100 rows, you can say, I'm setting aside 30 rows for validation, 20 rows for testing, and I'm going to use 50 for training. You can do something like that. And when you're training, you can use the validation test. Every time you actually train, you need to compare the error to something, right? So there is a training data that is coming in. And the training by itself has a cultivar, a while cultivar. Now, that is used for back propagation. But once you back propagate, while you do that, you also use an unseen data that the network that has not seen that on training, and you call that as a validation within that iteration or within that mini batch or after an epoch, and say validate it against this data set. That's a question you're asking, right? You validate against this data set. If you haven't, you go back to the epoch, you go back to the next mini batch if the error is still too much on the untrained. You never train on the validation data. Only the training data is being used for training the neural network, for supervised neural network. The validation is only used to say how far are you for the unseen. You've seen, and the seen data is actually being used by the backpropagation to scale the gradient. The unseen next comes in as additional input.
But let's say if you have real data when the network is in play and it comes across some sort of input which is very different than what is being seen, right? But it's very apt and should be classified. Then how is it handled? Like, it might be edge cases scenarios, things like that, but how
The network always chooses an output that you have asked it to choose. It's just that the output will be wrong, right? You can also set up a neuron which is other. There's no guarantee, so you can say cat, dog, others. So if it's mostly looking like a cat or dog, like even if it is not seen, it will probably say cat and dog and not other. And that species might not even be cat and dog, right? But if you send a hot dog, if you send a chair, a table, a horse, maybe it will say other. But there is no guarantee that the network will actually, kind of, if it cannot figure out between cat and dog, it will always go to other. It will kind of figure out something because you trained it to do something, right? But that said, you use those historical data points to train the network once again. So let's say you train the network on past 3 days of data. You deploy it today. You let it predict. Then you go to, it's tomorrow, right? Now you go back to the last day, what happened? You look at the prediction errors. You know that it's an error. It predicted something, but that did not happen. You predicted a click, but the click did not happen. You predicted a path for students to learn. They didn't take it. You recommended a document. They did not read it. You predicted that they will subscribe. They did not subscribe. So you have that difference. You go back and find out why that's happening and retrain the network. Deploy it another day, right? So you can have a moving window of training data. The partitioning schemes can be set up in such a way that you take a portion of this test data, set it aside. This is called a k-fold. You have multiple rows. You can actually partition the rows into k folds, and you can train the network by first setting the test data aside for the first fold and training on the remaining. That's the training. Next epoch, you train on you set the second fold aside and you train and validate. So you can do that. That's called k-fold. Or you also have leave p out, where you actually have p observations and you actually take a combinatorial approach of 30% as a moving window. That is, leave P out is I'm going to take these 3 out and train on this. Next, I'm going to take this 3 and train on the remaining. Next, I'm going to train on this 3, validate on this 3 and train on the remaining. That's a C. That's a lot of combinations. You don't need that. That's exhaustive. You can also do a combination C and 1. That's called a leave 1 out, right? That is also very exhaustive. Typically, what you do is a non-exhaustive k-fold, which is good enough for training. The next thing that you do is to reduce the model architecture complexity by itself. That is, you can come up with some thumb rules, and the thumb rules are based on what's the total number of layers that you need, right? So if you have 0 layers, it's a linear representation. Even if it's a nonlinear activation function, there's not much of interesting things that's happening in that layer, which is just one neuron. If you have one hidden layer, then you have some kind of quadratic learning. It can actually, in a single layer, you can only, fit a line. In 2 layers, think about you fitting a curve, right? With n layers or 3 layers and more, you'll start getting some polynomials. I mean, you can fit many different things. So that's the first thing that you have to remember in terms of what is it that I want to predict. If it's a linear regression, you don't need too many layers. If your output is quadratic, or if your input is quadratic, you don't need too many layers. But if your input is like a cat or so on and so forth, that's when you start requiring layers. If your input is a market index, which is a polynomial, that's when you need multiple layers. That's one thing that you have to remember in terms of model architecture, right? The second part is, what's the best way to find an optimal size, number of neurons within an architecture? You can go with a simple thumb rule. The thumb rule is take the total number of hidden neurons that I'm going to have is based on total number of samples that I have in my training data, that is ns, the size of the samples. Total number of input neurons plus the total number of output neurons that I have, and some scaling factor alpha. And that scaling factor alpha is something that you dabbled around with, right? So if you have like 1 million cat pictures, and if you have a 600 by 400 as your pixel dimension, that's the total number of input neurons. 600 by 400 is your input neuron, right? That's the total number of neurons that's coming in. And if your output is like 2 or 3, a species of cat, and the output is having X amount of neurons, you take a scaling factor somewhere between 2 to 12, scale it up, and say, okay, the number of parameters in my the number of neurons in my hidden layer will be some thumb rule like this. Doesn't always work like this. This is a simple vanilla feed-forward neural network thumb rule. And then you can determine whether you want layers primarily because you want to actually go ahead and demonstrate behaviors which has a decision boundary like that, which is I want to classify A and B like this, or I want to classify A and B like this, or I want a strict classification where I want both A and B to be identified correctly. That's called the decision boundary. So far, so good? All right. Small networks are faster to train, but they get stuck in the local minima because they don't have the complexity to model all the degrees of freedom. Large networks are harder to train, but they exhibit creativity, they exhibit complexity. They can actually find a global maxima if there is enough data, but they are kind of inefficient. You need to regularize them. Regularization means you want to make sure that they're not learning the noise. So what do we do? There are two approaches. One, you can actually start with a small network and see if the error is actually reducing. If not, then you start increasing the size of the network. That's called cascading up. Or you can prune down. You start with a very large network. If it's just having very high variance, then if you know it's variance, then you can start pruning it down.
Could you start with a small network and then train fast and maybe train 50 and just see if they provide the same solution every time to realize if you're avoiding one?
You can do that as well. So if you have 50 small networks, the degrees of freedom of each of the network is small either way. So all the 50 will land up behaving similarly without being able to pick up variances. So it will be low variance, right? And probably low bias as well. So when you try to average them out, you're actually trying to average low variance, low bias. The other thing that you can do as an ensemble is have networks of various size predict something and then average it out, right? Instead of cascading up or cascading down and trying to find one network, you can take networks of various sizes, let them output whatever, some output high variance, some output high bias, some output something in between, then you're trying to average it out. That's an ensemble you can do. That's a committee of machines, as you call it, right? You can also try to replicate that behavior in the same network using a concept called dropout. What a dropout does is it actually cuts the connection between two neurons randomly when you're training. Right? When you cut the connection, you are creating many networks in a single network. You're actually getting multiple networks. So first epoch, or probably first iteration, or first mini batch, you randomly choose 50% of the connections and you cut them. Next epoch, you again randomly choose 50% of the connection and cut them. You don't learn the weight. You don't forward signal. There's no transfer potential. When in a directed acyclical graph, when you're actually cutting these parameters, you're creating different networks. So the beauty of a neural network is you don't even have to create an ensemble by actually doing multiple networks. You just drop out. You drop out by X percentage, right? The other technique is called weight initialization. So when you actually look at the distribution of weights when the network is fully trained, it probably moves from here to here this way. It starts with some distribution. Initially it's randomly, think about it as some uniform random distribution or normal distribution. That's not uniform normal, that's normal distribution, multimodal. As you train, the weights actually is, not all weights. Initially all weights were close to zero, right? Somewhere. Not all, but they were close to zero. But as you train, the weight started moving towards, for whatever the activation function, I'm not saying what this training is about, but the weights has a characteristic to gain or to lose. That's what you're doing, is scaling the weight, right? And that distribution is what this is demonstrating. So knowledge is nothing but the ability to find that weight distribution, isn't it? The ability to learn that function of the input and the output is nothing but figuring out the weight distribution. Pretty much that's what knowledge is, that distribution of connections. What if you can somehow short circuit, you don't train, but somehow you can predict. You look at a lot of distributions of some trained networks, and can you just directly predict that and initialize the network in such a manner that you don't have to, the error is minimal right get-go. You understand what I'm saying? So let's say I have multiple possibilities. What if we start with all weights 0?
You don't learn anything.
There's nothing to learn, because the transfer potential is the signal, which is xi times w. Anything times w is 0, the entire network is going to be 0. That's not very interesting. If all the weight, if this line, if you've set up all the weight over here like this, and this is a very long line of all the weights, it's not going to learn anything. It's nothing. It's clinically dead, right? Sometimes it can be linear based on if you have a bias in there. If all the weights is 1, you set up all the weights, so you just move this line to the, then it's a linear network. It's just linear. Xi times 1 is xi. Xi comes in, xi goes out. Xi is the only one which is actually getting activated. Not very interesting. So you need a distribution. But you don't know how to initialize the weight. You cannot have all the weights to 0 or 1 or n or whatever. They cannot all be the same. So then you take a Gaussian approach. You say, I'm going to standard normal it. Or you say, I'm going to truncated normal. I'm going to clip it so that the weights are not too large. Because in standard normal, you have an asymptote. There are probabilities that certain weights can go to infinity on one side, negative infinity on another side. You don't want this. So you take a truncated normal saying, I want the weight to be between a and b, whatever that a and b is. You choose that a and b, 10, minus 20 and 20, or minus 10 and 10. And then you take a standard truncated normal and you initialize it. That's one approach. Another approach is you take similar models. That's called transfer learning. You take similar models which has demonstrated certain weight distribution, take that and boot your network with that and see what happens. The concept is called transfer learning. The knowledge is actually available somewhere in some other black box which did some other job. I'm going to start from that and start training that. Somebody has trained on another animal, ferret or dog or something. Maybe that animal that you're training is like the horse looks something similar like a dog, right? So I'm going to borrow the knowledge, the weight distribution of a dog network, initialize it, and you can start from there. I mean, it has its pitfalls, but, or you can use some other mathematical models, right? Are you with me so far? These weights are not just uniform or normal, they are multimodal. They're not bimodal, they're multimodal, where you see many modes, but mostly they are normal. So typically, instead of truncated normal or standard normal distribution, we use other techniques for weight distribution based on certain considerations. One of the considerations is called vanishing gradients. That is, when you have multiple layers, when you start training the gradients, when you start backpropagating the gradient, the layer which is closest to the output will always get the higher gradient. And based on that, you're trying to compute the gradient of the previous layer. Based on that, you're trying to compute the gradient of the previous layer. And those gradients will start getting smaller and smaller, and the input layer will actually get no gradient at all. So your gradient vanished. That's one consideration when you're doing weight initialization. When the gradient vanishes, the network doesn't learn, right? The second is exploding gradients, opposite of it, where if your activations are small and your weight, the size of the weight is extremely high, the gradient is steep. That means it can just, the velocity of the gradient is so high that it can, instead of trying to go down, it will start bouncing off without converging on the quadratic. If you can understand the geometric representation of it. That is, if the gradient is really high, it just keeps doing that. It will oscillate, it will not point like that. It's really high because the tangent on that curve is pointing into a very strong direction. So that's called exploding gradients, right? You don't want vanishing gradients. When the gradient vanish, there is no learning. You don't want exploding gradients because you never converge. So you take a heuristic approach. I do not know whether this is visible. I'm going to share the Is it visible? Not really. That is just 1 divided by size of the previous layer, layer minus 1. That's the variance calculation, right? That's pretty much what is over there. So here are two different initialization of weight. This is called the Xavier initialization. This is the truncated normal initialization, right? Notice that this is actually becoming this is layer 1, this is layer 2, this is layer 3. Most of the weights are converging towards a 0. And it's looking like a standard distribution. That's looking like a Gaussian. That means the network starts learning. As soon as the weight starts moving towards the 0, something's wrong with the network. So you should start visualizing your neural network. This is called tensor board. You can visualize your biases, you can visualize your weights. You don't blindly tune your network. As soon as you see something like this, network start learning. This is probably what you want to see. That either they're uniform or they're like multimodal, like in the last layer, right? So this is called the Xavier initialization. Exactly the same network, exactly the same number of iterations, mini batch, error functions, activation function, everything being the same. The trick of just initializing the weight differently actually has a different effect on the network, right? Any questions? All right. Then there is the learning procedure by itself. There is something called a learning rate that you can actually set to your gradient. You can actually apply the entire gradient. If you remember last time we said that the weight is a function of the delta, that is the gradient, plus the weight at time minus 1. Wt, which is the current time, is a function of the previous weight plus the gradient that you actually computed. This is what we did as a math, right? You can apply the entire gradient as is, or you can say I want to apply a little bit of the gradient and a little bit of the previous weight as well. It's not alpha and beta, it's epsilon and alpha. I'll show it in the next one. But I'm just saying if there are two variables, two scaling factors that you want to apply, you can use a couple of Greeks, put it as a coefficient and say, I want to scale it. I don't want to learn the entire gradient. I don't want to compute the entire weight based on the previous one. That concept is something that we will learn in the next slide. But that's going to help us in terms of generalizing your network better. That means it doesn't have to fit correctly. This I'm going to revisit because I know we're running out of time. This slide, this concept of scaling the learning rates and the momentum comes from a field called stochastic approximation or stochastic optimization functions. I'll revisit this math next time. The examples of stochastic approximation comes from applying the optimizations for places where precise mathematical models are hard to compute. So you use a approximate estimation of the parameters, which kind of models the complexity. So you do this when you want to estimate unknown parameters, when the sample is random, when the data is noisy. So that concept of not just doing gradient descent, but you do what you call as stochastic gradient descent. The stochastic approximation is where the gradient descent actually gets better. And this is the function of stochastic gradient descent. What has happened? So there are many, this is called the optimization function. There are many optimization functions. If you notice, there is SGD, which is stochastic gradient descent. You can also see momentum, Nesterov, Adagrad, Adam, whatever. Each one of it has a task to find the minima. Some of these are finding the minima faster, while some of the optimizers are getting stuck on the saddle point. The saddle point is a perfect point where a ball can be balanced in a hierarchical minima. That is, this is a saddle, right? But the minima is over here. But the gradient over here vanishes on a saddle point. There is one tiny dot over there where the gradient can vanish. And if you are actually learning too slow with no momentum, no velocity, for you to normally rest with no inertia on that point is extremely high. So you also don't want to learn really slow. You don't want to learn really fast as well. That means you're actually going to jump off the saddle. You're going to come really fast down and then you're going to bump up the saddle. So we use the concept of displacement, velocity, and momentum as our stochastic parameters to come up with a better gradient system. That's called stochastic gradient. Really not the best, but that's the first place we start understanding stochastic approximation. What's happening here? We're saying instead of just taking the derivative and the previous weight is left intact. Instead of just taking the derivative, what we're doing is we are taking the current derivative, applying an epsilon, which is nothing but a learning rate. How much of the current derivative, current direction should be considered, right? Which gives you what you call as a speed or the velocity. Because the gradient is saying this is how fast you need to go. You say, I want to slow down a little. I don't want to go really fast because I'm going to just go out of the saddle. I'm going to slow down a little. There's a dampening that's happening. But also you're saying how big the ball should be. When, if it's a really tiny ball, it doesn't have enough momentum. If it's a really large ball, it gathers momentum if it's coming from far, right? Which dampens the oscillation. You say, how do you control that? You actually use another scaling factor over here to the previous gradient. You retain the previous gradient, and you say the total gradient is based on the direction that I got from the previous gradient. So previous gradient plus current gradient actually tells me the momentum. Momentum requires at least 2 points, right? To say, what should be the weight of this ball. And then I'm going to take that, which is the scaled weights, stochastically scaled weights, and apply it to the current weight for scaling. In other words, there's a momentum, there's a gradient, but you use a combination of that to say, no, don't go in this direction, don't go in this direction, but here's where you need to go. So far so good. We're going to do the math of this in detail as we go forward. But that is the concept of stochastic gradient. The learning rate by itself, how much do you have to set? What should be the value of epsilon and alpha? You can actually, train and observe what happens to the error by changing the learning rates, if you notice over here, and figure out what should be the optimal learning rate. If what you need is that the learning rate should express the steepest decrease in your loss. As long as a learning rate you're set is actually expressing that steepest decrease, you say, okay, that's a good learning rate, that's a good learning rate. You want to keep it. But as soon as you start seeing this oscillation and when it starts bumping, that's really fast. That learning rate is increasing the velocity of your learning so fast that it's just bouncing off, it's oscillating. Then you want to scale back the learning rate. That's how you choose an optimal learning rate. So all these concepts are called hypertuning, hyperparameter tuning, right? You can also set it on an annealing schedule. You start with the highest learning rate. Highest learning rate means fastest, and start reducing the speed on an annealing schedule. I'm going to cover simulated annealing or logistic annealing at a later point in time. But think about it as stepwise reduction of your learning rate to find the optimal. Any questions so far? Eventually all of this should help you train your network better in terms of not learning the noise, learning the signals, and finding that optimal point. In this slide, I've actually given you a Tensor Playground link, which is available here. When I share the slide, click on it and play around. Typically what you will see is an ability to set the number of neurons, the number of layers, activation functions, error, learning rate in that dashboard. and typically see what the network is doing. How is it classifying a problem like this? This is a hard problem, right? I mean, if all the data points were, all the x's were on one side and all the y's were on another side, the decision boundary would have been clean. But in this one, notice that orange and blue are intertwined, and you are asking the network to come up with a plane which actually classifies it correctly. How many neurons you have? Literally a handful. Look at the power of this. Try to do this using classical machine learning, and you'll see the problem. So this dude actually fits it almost fairly well. It kind of gives you the orange region on the orange dots, blue region on the blue dots. You can see what happens to the error in the top. So look at the output. The loss function on the training loss is actually recorded here. It bounces off and eventually curves out. All of this is based on the concepts that you learned, which is activations, regularization, size of the network, complexity of the network, partitioning scheme of the data, holdout and validation sets, learning rates, which is your hyperparameters, all the Greeks, right? Which allows you to set up exactly the same neural network, weight initialization, and achieve this with, I don't think that's probably 400, 500 steps. It's not even more. And it allows you to visualize that. And this is running in a HTML page. This is not using some complex architecture. This is a JavaScript that's running. Any questions? I'm going to rehash most of this in the next one, where I'll actually go deeper into some of the optimization schemes. I'm going to get a bit deeper in terms of understanding variance and bias mathematically, so that we know what's happening behind the scenes. And then we're going to actually hand code. I'm going to come up with a Python code which shows how to classify the wine data set that we had. All right, questions? Was this helpful? Right on time. Trust me, I'm going to cover the same concepts in different ways. You're going to see different cat pictures, different training variations until you learn. I'm going to say the same things in many different ways, and multiple epochs, right? And we're going to learn. Good? All right. Thanks, guys. Appreciate it.